Thank you very much. Hello, everybody. Thank you all for joining us today in this lovely venue. My name is Nimrod. I am a security researcher at Plaxidity X, formerly Argus Cyber Security. And at Plaxidity X, we research and develop various cybersecurity products for the automotive industry. And my team is doing security research and consultancy for the automotive industry. In this talk, we will explore two vulnerabilities we identified in certain 32-bit PowerPC microcontrollers from STMicroelectronics and NXP. These vulnerabilities allow a privileged attacker to shut off memory protections even though they were properly configured in accordance with vendors' instructions. Our agenda for today is the following. So we'll start with an introduction to MPUs, some history, and MPUs functionality. Then we'll discuss the special role of MPUs in securing automotive applications. Next, we'll describe the most commonly used types of MPUs in modern industrial and automotive microcontrollers. Then we get to the technical part where we present the analysis of the vulnerabilities and talk about their impact. And next, we describe the disclosure processes we went through with the two vendors and attempt to analyze their responses. Eventually, we will offer some mitigations and concluding remarks. So here we go. We'll start with some history. So early microprocessor designs, such as the IBM System 360 from 1965 and the Apple Macintosh from 1986, already included memory management units, or MMUs, in them, for handling virtual memory mapping and memory access permissions. But it wasn't until 2004, with the introduction of data execution prevention, DEP, in Windows XP, and no execution bit, NX, in the Linux kernel, that MMUs were used as actual exploit mitigation to prevent execution of injected code from memories designated as data areas. Smaller microcontrollers, however, did not require the virtual memory mapping overhead of the MMU, and therefore they did not include MMUs in them. But one shortcoming of microcontroller architecture was the use of commonly shared memories for operating system, user software, and data. Applications that required a higher level of security, such as automotive applications, began implementing a downsized version of the MMU that only implemented memory access permissions specifically tailored to microcontroller architecture. And that was the beginning of memory protection units, or MPUs, as we know them today. So what's an MPU? A memory protection unit is a programmable hardware unit that acts as a gatekeeper of memory. At its basic configuration, it enables the system designer to divide the memory into regions, and for each of those regions, set memory access permissions, meaning who can access the memory, such as privileged processes only, privileged and non-privileged processes, or perhaps no access at all, and so on, and set memory attributes, meaning what type of access is allowed to that memory region. And here we may see read access, write access, and code execution access. So in very basic terms, MPUs oversee access control to shared memory resources with a stated goal of considerably reducing the attack surface of the embedded system. Now, why are MPUs so important in the context of automotive industry? Now, memory protection units play a significant role in the automotive industry by enhancing the security, reliability, and safety of embedded systems within vehicles. Firstly, just as much as any other industry, automotive systems certainly benefit from the advantages offered by MPU mechanisms. These prevent unauthorized access to memories, help minimize data corruption, and attempt to stop unintended code execution. Secondly, automotive ECUs, electronic control units, frequently use software components running at different privilege levels, such as HSM firmware, bootloaders, secure boot processes, all the way to third-party applications, which are regarded as least privileged. MPUs are best positioned for such challenges as they natively monitor both the privilege level of each memory access request and the source that requested that memory transaction. Thirdly, using MPUs, automotive safety applications, such as those assessed by the ASIL scale, defined in ISO 26262, can be allocated with their own memories, both data and code, while blocking access to other non-safety applications. This considerably reduces the risk of interference and malicious access between safety and non-safety applications and promotes the overall safety of vehicles. Many current automotive microcontrollers are today multi-core and may access common memory simultaneously. So securing memory accesses becomes a challenge. MPUs, as we said earlier, are source aware, and so they are perfectly positioned to deal with those kinds of security challenges. And lastly, automotive microcontrollers are usually heavily equipped with memory-intensive peripherals. Those are peripherals that can access memories independently of cores. For example, DMA, CAN network controllers, USB, Ethernet, and so on. Those also need to be monitored since they may be maliciously exploited to gain indirect access where direct access is forbidden to those commonly shared memories. Since MPUs, again, are source aware, they can just as easily secure this type of memory access to promote the security of automotive systems. The two main types of MPUs, this is what we're going to talk about now, used in the industrial and automotive domain are the core memory protection unit and the system memory protection unit. The core memory protection unit, also known as CMPU, core MPU, or CPU MPU, is integrated directly into each of the cores of a microcontroller and controls all memory transactions originating from that core. Cores can naturally read and write memory, but perhaps their main objective is to execute code from memories. And therefore, one important attribute of the CMPU, the core memory protection unit, is the execute attribute, which marks the memory regions that each core is allowed to execute code from. As we shall see when we get to the NXP PowerPC chip, some vendors integrate the CMPUs inside the system memory protection unit, or SMPU, to create an extended SMPU. The second memory protection unit is the system memory protection unit, or SMPU, and it is designed and positioned to protect the entire system memory space and is source aware. Each SMPU memory region has a list of allowed memory transaction sources. also called bus masters in PowerPC terminology, and their access attributes. Only those memory transactions originating from one of the allowed bus masters and with the required permissions and attributes will be approved by the SMPU while blocking all others. Same as other MPUs, upon violation of its permissions, the SMPU initiates a hardware fault which blocks the memory request and allows the system to restart itself, effectively shaking off the potential attacker. So now that we know the basic types of MPUs and their importance to automotive applications, we can start our journey towards configuring them. But unfortunately, to us anyway, there's no MPU configuration handbook. The book you see on this slide was generated by the Gemini AI chatbot, and it's not real. Consider the scenario of an embedded system designer tasked with the setup of an automotive embedded system and then the configuration of its memory protection unit. We'll take, for example, the STMicroelectronics 32-bit PowerPC that is the subject of this talk. That system designer would have to do a lot of reading, and I mean a lot. The system designer would have to start with this 452 pages of the enhanced PowerPC architecture manual, continue with reading the 390 pages of this PowerPC core reference manual, not a New York Times bestseller, I assure you. Then read the 147 pages of this chip's datasheet, and if all that was not enough, our poor system designer would have to get closely acquainted with perhaps the most important of them, the thrilling 1,439 pages of this ST reference manual. So far, we've reached more than 2,000 pages, but even if the system designer religiously follows all instructions in each of these manuals and datasheets to configure the PowerPC MPUs, a skilled attacker would still be able to disable the PowerPC SMPU and gain a foothold over the microcontroller. The explanation to this lies with the vulnerabilities we discovered and are about to share with you today. The two vulnerabilities are hardware vulnerabilities we identified in 32-bit automotive-grade PowerPC microcontrollers from STMicroelectronics and NXP of what we believe is a missing implementation of logic components on the silicon. These vulnerabilities allow a privileged attacker to shut down the SMPU and gain read and write access to previously protected memory regions. And on the NXP chip that we'll see later on, read, write, and execute access to previously protected memory regions, even though the SMPU was properly configured in accordance with vendor's instructions. Consequently, the system designer remains under the impression that their system is protected and secured, completely unaware of the underlying risks. So we're going to start with the STMicroelectronics PowerPC chip analysis and later explain the differences with regards to the NXP chip. We will focus on this SPC58 chip family, which is an automotive-grade microcontroller throughout the analysis. Other affected parts, as reported by STMicroelectronics, are listed on this slide. And now we're going to together open the SPC58 datasheet and take a look at the block diagram. So here it is. This is again the SPC58 PowerPC 32-bit chip from STMicroelectronics. It has the common memories at the bottom of the diagram. They're connected through a system bus to the top of the diagram where we can find the cores. Let's zoom in on the bottom of the diagram. Here we can see at the left-hand side the two static RAMs in blue, and on the right-hand side 4 megabyte flash and the EEPROM. These are the commonly shared memories. At the upper part of the diagram, in the blue shaded blocks, are the chip's cores. Let's zoom in on one of the cores. This STMicroelectronics PowerPC has 3 cores, and as we can see in each and every one of them, we can find a core memory protection unit, or a CMPU, there in red. The CMPU configuration is pretty straightforward, and we're not going to go into details about it here. It is enough for us to say that it is pretty well secured at this point. Having said that, next we configure the chip's system memory protection unit, or SMPU. Let's zoom in on the SMPU now. So, as we can see, the SMPU is positioned in between the cores and the shared memories, and we marked it in yellow. To configure the SMPU, we should set its region descriptor registers, namely start address and end address of the memory region we wish to protect. On top of that, and as we said earlier, the SMPU is source aware, there's also a list of allowed bus masters and their attributes that we need to configure. So the STMicroelectronics reference manual has a list of available SMPU bus masters, which we're going to look briefly now. So we have a total of 16 bus masters here, although only 14 are actually used. Let's go over the list quickly. The first 3 bus master numbers 0, 1, and 2 are the 3 cores. Then we have a DMA controller, Ethernet, FlexRay, which is a high-end automotive network, a multimedia card, the debug ports, which each of them is connected to one of the cores, and eventually closing the list is the HSM core at busmaster number 14. Now we're getting down to business and actually setting up the SMPU. This is the region descriptor word 0 register. And here we define the 32-bit start address of the protected memory region. Next we have region descriptor word 1, which defines the end address of the protected memory region. In this region descriptor word 2, we have the list of bus masters for the specific memory region and their access attributes. Each bus master has its own read and write attributes, specified using 2 bits. These bits definition are listed in the table on the right-hand side of the slide. Let's take an example. Let's say that the system designer wants to allow only the HSM core to access this memory region for reading and writing, while blocking all other sources or bus masters from accessing this memory region. To do that, we write 1 into bits 28 and 29, which are busmaster's 14 access attributes, which allows the HSM core full access to this memory region for reading and writing. Setting all other busmaster's attributes to 0, 0 blocks all other masters from accessing this region. Once all regions of the SMPU are configured, we should start or enable the SMPU hardware mechanism. This is accomplished by setting the GVLD, or global valid bit, in the control error status register CSR 0 to 1, and effectively starting up the SMPU. However, before we actually enable the SMPU, we need to pay attention to another important SMPU register. Let's go back to the reference manual. This is region descriptor word 3, and here we find the arrow bit, read-only bit, which is marked in green. This read-only bit is used to prevent unintended or malicious manipulations of the region data that we just configured. The start address, the end address, the allowed bus masters, and their attributes. When the arrow bit is set, write operation to any location within the region descriptor registers are simply ignored. That's perfectly understandable and important from a security perspective. But I'm not sure you can see, there's also a note with the arrow bit description in red. Let's zoom in on the note. The note says that once the arrow bit is set, all region descriptors are locked and cannot be written over. We understood that. Until a system reset. Also, the note adds, once the arrow bit is set, the global valid bit, the GVLD bit we just discussed, will have no effect, meaning the GVLD bit cannot be manipulated and the SMPU cannot be disabled until the next system reset. This looks like a smart defensive trick. I mean, there's no use closing the window while leaving the door unlocked. After the next system reset, an attacker would lose any grip they had on the device under attack and allow the system to reconfigure itself back to its original state, effectively shaking off the attacker. So next, we wanted to test and see how this elaborate SMPU security mechanism works and perhaps learn from its implementation. To do that, we set up a POC with the relevant chip. We set up the hardware, we set up the CAN communication, we connected a JTAG debugger, and powered up the system. Then region descriptors were programmed, 32-bit start address, end address, allowed bus masters and their attributes, and after that, RO read-only bits were set, so all region descriptors were locked, and the GVLD bit was set to 1, and then we started testing the system. We simulated an attacker on one of the cores of the microcontroller, and we soon found out that although the manuals of the SPC58 claim that the GVLD bit would have no effect on the SMPU after the RO bits are set, for some reason, this hardware mechanism, to the best of our understanding, was not implemented on the silicon, or at least it wasn't working, and therefore a privileged attacker can disable the SMPU by simply writing 0 to that GVLD bit in the CSR0 register, as simple as that. This would allow access to previously protected memories for both reading and writing. So that was our story with the adventure we had with the STMicroelectronics PowerPC chip. And after the discovery of the SMPU issue, we kept on looking for similar PowerPC implementations to see if we can find other PowerPC automotive-grade microcontrollers that exhibited the same issue. Well, we came across what seemed to be a similar architecture in this NXP formerly Freescale MPC5 family of PowerPC microcontrollers, which chose a specific NXP PowerPC variant, the MPC5748, which is an automotive and industrial control microcontroller. And we wanted to see if this PowerPC from NXP holds a better security posture than the STMicroelectronics chip as far as the MPUs are concerned. So again, we're going to start with the datasheet and the block diagram of the NXP chip. So this NXP PowerPC houses 3 cores. We already zoomed them in yellow. It has also flash and static RAMs in green. But just looking at these cores, we were wondering to ourselves where the core memory protection units, the CMPUs, are. None of these cores, and you can see for yourself, is protected by a CMPU. It seems that this microcontroller only has a system memory protection unit, or an SMPU, there in red. We kept further investigating, and we soon found that the NXP SMPU also contains the functionality of all the CMPUs that were supposed to be inside each of the cores. This means that if the same weakness that we found in the STMicroelectronics SPC58 chip exists here in this NXP microcontroller, a privileged attacker would now be able to completely disable the extended system memory protection unit, and by flipping the GVLD bit, effectively gain read, write, and execute access to previously protected memory regions. So we started reading through the reference manuals of the NXP chip. The NXP register names are quite similar to those of the STMicroelectronics chip. Again, we see the global valid bit, which is located in bit 31 of the CES0, quite a close name to the STMicroelectronics, the CES0 register. And surprisingly, we also found a similar read-only bits, only here they are called LCK bits. Let's look at these. So in region descriptor word 5, we find the lock bits, and their functionality is quite similar to the read-only bits. They lock the region descriptors against writing once they are set in order to prevent manipulation of the region information. And as you can see there in red, there's also a note. Let's zoom in on the note. Here the wording is almost identical to that of the STMicroelectronics chip. Once you lock the regions using the LCK bits, the global valid bit of the SMPU has no effect. So the SMPU cannot be disabled anymore until the next system reset. Another short test we conducted right after that revealed that although the SMPU is enabled and all lock bits are locked, LCK bits, a privileged attacker can still flip the global valid bit to 0, and by doing that completely disable the now extended SMPU, which is the only effective memory protection unit in this PowerPC chip. Since there are no separate CMPUs, by disabling the SMPU, an attacker gains read, write, and execute accesses to all previously memory protection regions. That was the analysis of the two weaknesses and their impact. And of course, we proceeded to notify STMicroelectronics and NXP about those issues with a responsible disclosure. So after finding about the weakness, we contacted STMicroelectronics product security and response team with all the relevant information about the weakness. After some back and forth correspondence, STMicroelectronics acknowledged the issue and said they would release an errata. But they claimed that the SMPU was not a security mechanism. Here is their response, and I'll read it from the slide. The behavior deviation of SMPU you detected may affect non-secure device domains. However, this domain should not be used for storing security information. Security information shall be stored within the HSM subsystem. If stored outside, they need to be encrypted. And of course, they added, the SMPU is not a security protection mechanism. Rather, it helps to avoid interference. Well, we cannot agree to that, of course. As we said already during this talk, without MPUs, data used by one application, for example, a safety application, may be read or manipulated by other non-safety applications to cause the former to behave differently than was intended. Stack buffers may be manipulated. Application code pointers may be hijacked to gain code execution control, and so on and so forth. We strongly believe that encrypting all this information is simply not feasible. Next was the NXP PowerPC chip. Again, we contacted NXP. After some back and forth correspondence, NXP acknowledged that documentation was not clear and said they would release a documentation errata. We're still waiting to see exactly when they publish it and what it's going to be. As was the case with STMicroelectronics, NXP also claimed that the SMPU is not a security feature. Again, I read from the slide quickly. The product reference manual is clear about the SMPU not being a security feature. How is it clear? The SMPU is not mentioned in the chapter Security Overview, nor in the section Security Modules, but rather in the section on System Modules. The SMPU is also not listed under security in the feature list table, and the chapter that describes the SMPU does not mention security. Well, as much as we read through the reference manual of the NXP chip, we could not find a positive reference to the fact that the SMPU is not a security mechanism. What again seems to us to be a totally given that it is. So I guess that eventually we don't see eye to eye with the two vendors regarding the SMPU being or not being a security mechanism. To summarize, as we've shown throughout this presentation, memory protection units are a crucial part of every microcontroller defense strategy, since they offer efficient and straightforward protections against advanced security threats. Moreover, MPUs are indispensable in the context of automotive applications because they enhance the security, reliability, and safety of embedded systems within vehicles. Frankly, since this is a hardware issue of what we believe is a missing implementation on the silicon, we don't think that fixing its root cause is feasible. We can, however, offer the following mitigations. First, make sure you test and verify all important claims made in datasheets and reference manuals, especially those that involve important security mechanisms such as MPUs or memory protection units. Second, always make sure to use stack smashing mitigations, for example, stack canaries. This is another way of preventing buffer overflow vulnerabilities from becoming arbitrary code executions. And thirdly, only for the STMicroelectronics chip, use as much as possible the CMPUs, which are much harder to disable than the SMPU. And of course, we cannot say the same for the NXP that uses the extended SMPU without a CMPUs. It is therefore extremely difficult for us to accept NXP and STMicroelectronics' claim that a hardware mechanism designed to enforce access control rights over shared resources, such as the memory protection unit, is not a security mechanism. Thank you.
Thank you very much for this great talk. Now we have time for some questions.
Thank you for the talk. I wanted to ask on the NXP chip and also the ST chips, would it be possible to use another page of the SMPU to protect the GVLD bit as a countermeasure?
That's a good question. The thing is, if you can, let's say you have 3 SMPUs, and you say the third will be protected by the second, and the second will be protected by the first. But you can, if you have access into the system and you find a rope chain, you can cancel the first, then cancel the second, then cancel the third. So the answer is no.
So I mean, instead of protecting just the GVLD bit, the entire SMPU peripheral would have a address range, correct? Can't you protect the entire address range of all of the SMPU peripheral?
Okay. I understand the question. It's a good question. With the NXP, you can't because you only have SMPU. So that's out of the question. You can, however, do that with the STMicroelectronics chip because you have cores. You have the core memory protection unit that can protect areas of the common memories or the entire system memory space, as we say. However, a skilled attacker would then be using one of the independent peripherals that I was talking about. So they can use the DMA, for example, to write into the GVLD bit and cancel whatever there is to cancel. So the answer again is unfortunately no.
Hi, thanks a lot for the great talk. I was wondering, I'm not really into the PowerPC ecosystem, so maybe this is a silly question, but does IBM provide in their guidance to implementers of the PowerPC ISA any guidance on implementers whether or not to use SMPUs, and if so, in what context?
Again, a very good question. To the best of my understanding, the IBM PowerPC is a different beast than these specific PowerPC 32-bit PowerPCs that are used in automotive and industrial control. The IBM PowerPC ISA, as you say, is more designed for the desktop, perhaps, computers. And these are something that these companies, they took and they created their own beast out of it. But so therefore we did not look into the thousands of pages of IBM information, but we only concentrated on the industrial and automotive PowerPCs. So
PowerPC ISA licensees are free to do whatever they want in their implementations?
To the best of my knowledge, yes, but I haven't been a licensee, so I don't really know. I think that they can, as we saw here. These are quite similar implementations. We don't think that they happened independent from each other. So there had to be some perhaps another company, I'm not sure what it was, that started it. And then somehow they separated into the two companies.
I see.
To the best of our knowledge.
Great, thank you.
Okay.
Any more questions?
Thank you very much. Two questions. I haven't looked up the CVEs. Are they in theory remotely exploitable? Is one. And the other would be, you mentioned that the chips are widely used across automotive as well as industrial control systems.
Yeah.
What about industrial control systems?
We are not in that industry, so I don't have specific numbers. I wouldn't want to go into numbers or anything relating to what's out there because it's a matter of safety and human lives. But you can find online millions of these chips going into different vehicles used around the world, I would say. About the CVE, in order to exploit this kind of issue, you would need a prior exploit to do that. You need access into the system. So we're not really going into this, but to exploit something like that, like an MPU issue, you would first need access into the system, and then the first thing you do if you're an attacker is you look for ways to cancel the MPUs, because the MPUs are what's holding you from taking advantage of the vulnerability you found of becoming arbitrary code execution, because you cannot execute. If, for example, you have a stack buffer overflow, you can write bytes into the stack, but you cannot execute them because CMPUs would not allow you to execute that if they're, set up, and I hope that they are. Then the CMPU would not allow you to execute code from the stack area. So the first thing you do when you're an attacker and you attempt to exploit a vulnerability that you have is to disable the MPUs. And in this chip, unfortunately, it's too easy.
Right, we're almost out of time. I think there's one last quick question.
So maybe not a big question, but maybe comment. In x86 there is no.
Can you?
In x86 there is no problem with treating MMU or MPU issues as a serious problems, and they escalate quite quickly and fixing stuff. So maybe this was problem with informing then and way of informing, and they essentially quickly thought about liability of potentially of that stuff, and that's why claiming this is not a security, but still the component does not provide what it should provide. Does not provide protection. So
x86 is I think it has MMUs in them,
and MMUs.
But yes, probably. I mean, we're not really going into the details of why they say. I think we understand why they say what they're saying. Because again, as you said, it's a huge liability when they have millions of these out in the streets. But then again, it is an issue that we see ourselves as the people that should be talking to the community about this issue. So.
All right, if there's more questions, you can talk to the speaker later. Let's thank the speaker again.